We're going to talk about scalar evolution. Scalar evolution is analysis implemented in LLVM. Many optimization passes depend on it. However, it's also a bit shrouded in mystery. So in the next 45 minutes, we are going to read through it very carefully, like a mystery novel, and try to solve this mystery. I'm going to start with some very basic examples to see what scalar evolution can do. However, to get further into what it can do, what it cannot do, we really need to look at the mathematical framework on which it depends. We'll do that, and now with that mathematical insight and perspective, we'll be in a better position to look at the SCEV or scalar evolution implementation in LLVM. We'll be in a position to appreciate its glory and criticize its limitation. We'll see how SCEV is used, how it's intended to be used, and it's how sometimes misused. And then we'll wrap up with some additional topics that we didn't cover so far because it didn't fit into the narrative, but are also in and around SCEV and important. Right, so let's get started. Many months from now, if there's just one phrase that you remember from this tutorial, hopefully you remember more, but if there's just one phrase, it should be this. Scalar evolution is a change in the value of scalar variables over iteration of the loop. So it is a study of the change, a systematic change in the value of a scalar as it goes through iterations of the loop. It's a powerful symbolic analysis technique, so it uses something like algebra for transformations. It can handle unknowns and symbolic variables stuff. The LLVM SCEV is a practical implementation of this mathematical concept. By practical, it also means it's not implemented in its full glory, but to the extent that it is useful and optimization passes can leverage it to give good gains. Many optimization passes use it. There are big users like loop strength reduction, vectorizers, induction variable simplification, and some other ones which use it in a limited way. So scalars and loops, we've talked a bit about it. Let's look at an example. In the beginning, there was a loop and a scalar variable, t. So t enters the loop for the first time, let's say with value 0, and every time it goes through the loop, its value increments by k. So that's the evolution of t. So it starts with 0, k, 2k, so forth. Now if you look at the code at the top, the only value of t that's really used is the last final value that is stored to the location a, pointed to by a. Is there an analysis that can figure this out and store the final value nk to a? Let's have a look. So this is LLVM IR for the same. Just focus on line 4, the grayed out area. There we see that we still have a for loop, and it's doing an add t plus k and storing the final value in the line 8. So it's still doing all the computation. But after induction variable simplification, after that pass has run, it has figured out with the help of SCEV the final value of t, which is n times k. If you look at 2 prime second from the bottom, that's the final value. That's all it computes, and it stores it to a, and it throws away the for loop. So that's one use. Okay, let's have a look at another one. Now in the previous example we saw t, it was all laid out very nicely. We had variable t, it was evolving. In this it's slightly more complicated. We have I times k. So the value of I, the expression I times k evolves from 0 to k to k, and these values are stored to the array a. Is there an optimization that can convert this multiplication to something like addition, so that which is a few cycles less on certain processes, let's say. Let's have a look again. So this is the LLVM IR for it. So here we see it's still doing a multiply. If you look at line 4, it's doing I times k. But after loop strength reduction, which uses SCEV, it has converted the multiply to an add. So it has created a new induction variable. If you look at line 3 prime at the bottom in the green box, it's iv underscore ik, that's a new induction variable that has introduced. And it is, if you look at line 6 prime right at the bottom, it's doing an add between that induction variable and k. So basically it's converted the multiplication to an add. Okay, so far what did we see? We saw loops, some induction variable, and passes that can use it in some way to reduce computations, right? What more can it do? Now to answer those questions, what it can do, what it cannot do, we really need to now look at the mathematical framework, and it's called chain of recurrences. We'll start with something that we are already very familiar with, which is induction variable. And start something more basic, the basic induction variable. A basic induction variable is a scalar that goes through your loop, and every time it increases by a constant. The simplest legendary one is the for I equals to 0, I less than n, I plus plus. So I is your basic induction variable. It's also your loop induction variable. It starts with 0 and increments by 1 every time, a constant. A generalized induction variable is a generalization of that concept, where the update is not by a constant. It may be a combination, a linear or non-linear combination of other induction variables, or basic or generalized induction. And it might be updated multiple times. So basically a complex kind of evolution of scalar variables in your loop. Chain of recurrence is a formalism, is a mathematical concept to analyze this kind of induction variables and express them as recurrences. What are recurrences? Actually, we know one example of it because we studied it a long time ago in a classroom perhaps far away, and that's factorial. So if you wanted to compute a factorial, n factorial is 1 times 2 times 3 up to n. Another way to do that computation in a more efficient way is to define it in terms of itself. So n factorial is also n minus 1 factorial times n. So that's a recurrence, and the chain of recurrence concept is an application of this similar concepts with respect to induction variables. Let's have a look. We'll start with something very basic called basic recurrence. So suppose you have k0 and k1, these are loop invariants. So these are maybe constants or symbols, but they don't change inside the loop. And you have a scalar f. So f starts with k0, and every time in the loop is incremented by k1. Now you can think of f as also a function where over I, where I is not really another induction variable, but your trip into the loop. So the first time you enter it, so I equals to 0, the value is k0. Every time it goes around the loop, its value increases by k1, so for I greater than 0. And that leads us to the notation for basic recurrence. So this is a good time to get familiar with this notation because SCEV uses a lot of it, and this is a basic recurrence. So it starts with brace, k0 is the start value, comma, plus the operator on which modifies it, and k1 is a step over I. So it starts with k0 and increments by k1 every time. Let's look at an example. So we have a basic recurrence, 3, comma, plus, comma, 7. So it starts with 3, and every time gets 7 added to it. So it will generate the sequence 3, 10, 17, and so on. Right? That's how it's going to look. And if you want to express it in terms of function, so fi is 3 for I equals to 0, and every time increments by 7. Right. Let's look at the example again that we saw earlier towards the beginning. So we have here I times k, that expression. Let's look at what LLVM SCEV really does. We run it through opt, analyse, Scalar Evolution. So this is, you can run it in this way, and it will just dump you, do the analysis and tell you what SCEV expression it has computed. And lo and behold, yes. If you look at line 5, you really have 0, comma, plus k. So it has taken that expression I times k and analyzed it and converted it into an abstract form called a recurrence. And the recurrence for that expression I times k is 0, comma, plus k, right? Okay, so we understand what is basic recurrence. What is chain recurrence? Well, it's actually more of the same. So if we understand basic recurrence, chain recurrence is not that complicated. It's a recurrence where you still start with a basic recurrence. So let's just focus on F1. So starts with 3 and increments by 7 every time. That's the basic recurrence. The chain recurrence is where this increment or the step is another recurrence. So F0 is the whole chain recurrence that we see here. It starts with 1. So when I equals to 0, F0 I equals 0 is 1. And the increment every time is by not a constant, but by another recurrence, which is F1. Okay, if you don't grasp all of it right now, don't worry. There are lots of examples coming because this is a tutorial, right? Just a bit on notation. The chain recurrence that you see at the top, I've just copied at the bottom and removed some of the braces because that's what LLVM SCEV does. Instead of putting tons of braces, it rewrites it like that, so it's as long as you know what it means. So these two are equivalent. Okay, so I promised you we're going to look at more examples to see this chain of recurrence and everything. So let's look at an example. And this example looks a bit complicated, but it's not once we have run through it. I've made it complicated enough so that it can show the flavor of this chain of recurrences. So it's just complicated enough to that extent. So we have x. X starts with 0, 1, 2, 3, 4, 5. That's your basic loop induction variable, and it's pretty straightforward. That's the basic recurrence. What is the recurrence for px, that polynomial you see at the top, x cubed plus 2x squared plus 3x plus 7? How do we calculate the recurrence for that? How would the compiler calculate the recurrence for that? I'm going to show you a method which is very straightforward. It's based on differences. That's not what LLVM SCEV does. LLVM SCEV does something more sophisticated, and we'll see that first. But this one is much easier to understand and relate to. So we do that first. So px, if we just took the calculator and computed the values, so when x is 0, all the x's are 0, so you have just the constant 7. That's what the value of px is. When x is 1, you can do the math, and it's 13. So this is just showing the computation if you just directly compute it. We take this, you take the difference. So if you take 13 minus 7, you get 6. 29 minus 13, 16. So it's the difference of the successive terms of px. Okay? We carry on, we take the difference of the difference. So delta square is the difference between the successive terms of delta. So 16 minus 6 is 10, and so on. We carry on, and we end up with 6 all the way. Now, it's not a coincidence. Because we started with a cubic equation, if you do the successive differences, you will end up with a constant at one point. Right. Now, so what's the magic? What do we do? If you take the starting values, that's your chain recurrence. With the chain recurrence 7, 6, 10, 6, you can reproduce all the values of this polynomial px. The polynomial is cubic, and yet you have this series of numbers that can produce all the values of this polynomial. You don't have to trust me. We're going to go and actually do it and convince ourselves. Okay? So what I've done here is I've copied the recurrence at the top, the values that we compute directly at the bottom, px, so you can verify 7, 13, 29, 61. That's the numbers you want to get. And can we compute it from the recurrence at the top? F0 is the recurrence that we need to look at. That's px, the green bar on the left. The rest are all the chains that we have there. So 7 is the first value. Yeah, it matches with the one at the bottom, F00. The second, so that's the value you enter the loop with. The second iteration of the loop, 6 gets added to 7, and you have 7 plus 6, 13. Now F1 itself is a recurrence. So you add F1 plus F2, that's 6 plus 10. So 6 plus 10, and you get 16, and so on. F3 is a constant. It's not a recurrence, so it remains constant. So carry on. 16 plus 13, you get 29, and yet it matches with the value here, and so on. And yes, indeed, we get the values that we needed, just using the recurrence here. So that's what this chain of recurrences does. And there are mathematical formulas that you can apply, we'll see later a bit, where you can compute the value at any point. You don't have to go through the whole step. You can directly compute the value that you need. So for example, if you want to calculate the value when you exit the loop, that's all you care about, so you can compute it directly. Now if you took the recurrence, that function and pass it through the LLVM IR and did the SCEV analysis, what does it give? This is what exactly you would see if you ran it through opt, scalar analysis, the recurrence that we looked at earlier. Okay. Now at this stage, you could in effect write this code where this polynomial is computed with absolutely no multiplication at all. So, good point to summarize a bit. So what have we looked at so far? We have seen basic recurrence. It has a start value and a step. Very simple induction variable, basic induction variable. Chain recurrences are where you still have a start, a constant, and a step, but the step could be another recurrence, and so on and so forth. So we saw basic recurrence, chain recurrences. We saw what do they roughly mean. We haven't yet seen how you get from LLVM IR to chain recurrences. We'll see the rest of that. At this stage, okay, it seems if we have a loop like that and some expression, we want to get the SCEV analysis for it, and we get this recurrence. Now, these recurrences are, why are they important? Because many of the passes, they find it much easier to work with something like this compared to something like that. Now, in this case, of course, that's pretty straightforward, but like in the previous example, when you have this cubic equation, the recurrence is much, much easier to work with. So, with that background, now we are going to look at LLVM SCEV implementation. So we'll have a running example, and that is not very complicated, but not too trivial. So k plus I is a loop invariant here, loop variable, sorry, plus I times p is loop invariant, and k is missing. Yeah, sorry, yeah, it's a short and great. I thought I messed up. Okay, so the first one, I. Now, what LLVM SCEV will do is going to go through your LLVM IR, look at the phi node, say, okay, phi node for I starts with value 0, and it has a back edge, and that's increment. And what is increment? Oh, it's I plus 1. So, okay, I figured out. The SCEV for I is this. Starts with 0 and goes increments by 1 every time. Okay, that's the SCEV for I. But what's the SCEV for k plus I times p? Now, we are not going to use the difference method and stuff, right? We want something more elegant. Now, to go from there to all the SCEV expressions, it uses something called rules, a bit like algebra identities that we learned in high school. I'm going to derive one of them for you, for us, to get a feel for it, and then I'm going to dump all the different equations that are there. So suppose I have a loop, and I have a very scalar induction variable I. It starts with 7 and increments by 3 every time, and a j, which is a separate variable, scalar variable that evolves. It starts with 1 and increments by 1 every time. And the value that I really care about is k, is I plus j. Okay? So we run through. The first time I will be 7, j will be 1, and k will be I plus j, which is 8. Okay? Next iteration of the loop, 7 increments by 3 becomes 10, j by 1, it becomes 2, and k is 10 plus 2 is 12. We carry on. Now if you step back and say, okay, so k starts with 8, and every time increments by 4, right? So For k, I can write the recurrence 8 plus 4. And it's no coincidence. 8 is 7 plus 1, and 4 is 3 plus 1. And in a not mathematical way, because we just use an example, this doesn't mean it's really mathematically tight, but we get a feel that, yes, if you have two recurrences, you can simply add the base and the step. That's one example, and for all the recurrence types that you can think of, you can derive such formulas. We looked at this one. If you have a loop invariant G and a recurrence, so if you're computing something where one is a loop invariant comes from somewhere outside the loop, and you have an induction variable or some other kind of variable that evolves, you can just simply add them and you get a new recurrence. In effect, what happens is you have these massive recurrences that you have calculated, and you can fold it up nicely into a form that the parsers really love to work with. That's the folding of SCEV expression. So we go back to the example we're looking at, k plus I times p. We computed the SCEV for I. Now let's do it for the rest. So this is the LLVM IR. We see the I plus k. K was short, so it's got sign extended to 32-bit because it wants to do arithmetic on it. And then there's a multiply and stuff, okay? Let's see how LU SCEV just goes step by step and computes the SCEV expression for it. So it starts with k, okay, sign extended, that's nothing much more there. And I, it has a SCEV expression, this is recurrence. It wants to do an add. So then it just folds k into the base here, and that's the recurrence for k plus I. Then we need a multiply, again using the same formulas that you can derive yourself if you are not convinced. If you're multiplying p by this recurrence, you just multiply through, and it's the equivalent thing. So what have you seen so far? We saw what was basic recurrence, chain of recurrences mathematically, and we saw how SCEV can just step through and calculate the recurrences for all the expressions that you have in your LLVM IR. If you recall this expression we started in the beginning, the cubic equation, and at that point we were looking at the difference method. We said to delta, delta square, delta cube, and we got the recurrence for this one. We got it at something like this. That's not what LLVM SCEV will do. As I said, it's going to take this x, take the recurrence for it, and simply apply the formula and get to this point. That's what it's going to do in this computation. Now, we look at the power of SCEV. This is high school algebra. I plus 1 whole square is I square plus 2I plus 1. Okay? If that's the case, then I plus 1 whole square minus I square minus 2I is 1. Yeah, why am I telling you this? Okay, suppose we have a program and a for loop, and I'm storing to AI, I plus 1 whole square minus I square minus 2I. What am I storing to A? I'm storing 1. But for some reasons, so you wouldn't write something like that, but it's possible, like in your actual program, somehow ends up that you have an expression that's massive, but actually it's computed to something very simple. Can SCEV figure it out? Let's have a look. So at this stage, this is LLVM IR after some initial passes have run, and they didn't do a good job. So it's still doing an add, so it's doing I plus 1 here, it's doing I plus 1 whole square. It has done some refactoring, so it's doing not I square plus 2I, but I plus 2, and then multiplying it out. Yeah, things very marked. And then doing a subtraction. So it's doing everything. And then we run SCEV analysis, and let's see if it can do a better job. So it computes this SCEV for I, which is just simple loop invariant, loop induction variable. So it starts with 0 and increments by 1. It folds 1 into I, so I plus 1. So I plus 1 would be simply the base increases by 1. It's just applying the rules. I plus 1 whole square gives you a chain recurrence. And then it does a 2 plus I and stuff, okay? magic is the last step when it's doing the subtraction. So it's doing analysis. It's not actually written out the new code, right? It does this analysis and comes to the conclusion, which we knew upfront, that the final expression is just 1. So what does it do? After induction variable simplification, which uses SCEV, we see that code simply stores 1 to the array. So that's powerful. Okay, change of gear a bit. We looked at basic recurrence, chain of recurrences, the power of SCEV, but so far we were just looking at one loop. What happens when you have nested loop? Okay, not much changes. So I'll just give a brief view on this. So if you look at the array expression for B, so you've got I and in the first index and j times j. We're going to just look at the SCEV for this expression B. So over I, because it's a char 100 by 100, so every time I increases by 1, your pointer increases by 100. So that's what you see down here. And because it's j times j is a chain recurrence, so you have this part here. And you can ask SCEV like SCEV at scope. So you want this recurrence at I or j, and it gives you the equivalent expression. Now a bit of word on the SCEV if you want to use it in your pass. So it provides a bunch of APIs. The first one, most important perhaps, is the get SCEV. So if you pass it a value or instruction, it computes the SCEV for the loop. So it has to be within a loop that it can analyze and stuff, and gives you SCEV expression. That SCEV expression you can take to SCEV expression and add them up or multiply. Depends what your pass wants to do. So what you want to do. So these are the APIs it supplies. Internally, it has these different expression classes, as you could have guessed. The most important one is the SCEV add recurrence expression. The rest is quite explicit. There are times when so for example, if you have a function and it returns you a scalar value, you call a function inside your loop and it returns you a scalar value. What can you say about the evolution of that scalar variable? Not much. It could be a random number generator, right? So that's an SCEV unknown would be. You can't say much about that value. To SCEV, because the way the SCEV works is doing semantic analysis of what you are really computing, not how you're computing. So if you end up to two expressions that are exactly the same value, you can do the comparison and it will point you to the same SCEV expression. So that's, you can do equivalence checking there. Okay, so after quite a bit of SCEV basic and chain recurrence and stuff, we're going to take a commercial break and talk about loops. So why do we want to talk about loops? Because a lot of passes that use SCEV restrict themselves to loops because that's in which they can operate and make a impact. But not any loops or every loop. Natural loop. So natural loops are those where you have a single entry point and no side entries. If you think about it just a bit, it would be pretty difficult, if not impossible, to calculate a SCEV expression where you could have a path coming from the sideways, right? Now, most optimization are not just happy with natural loop, they want even something more simpler, and that's canonical form, where you can actually, there is an API, you say, is simplified form, it's also known as simplified form, you can check. So what is a simplified loop? It has three things: a pre-header, so you can artificially create a pre-header. So if you wanted to hoist something out of the loop, if you did that in here, you would have 3 places to go and hoist the code. If you have a pre-header, you just move it out of the loop into here. Second thing about a canonical loop is a dedicated exit. So if you want to sync code out, you don't want it to be executed in the wrong path, so the external path is down here. And the third thing is a single package. If you had multiple packages, it's going to refactor it. So these are transformations that you do to a loop that passes can use. So end of commercial break. We're going to go back to SCEV, and now we're going to look at SCEV users. So what are the parsers that use and how do they use it? So you could first look at loop strength reduce. It hoists loop invariant computations that it has figured out, let's say with SCEV analysis, out of the loop. The first thing it checks, and that's why we looked at loops, is it checks whether the loop is in a normal form, is in a good form. So it checks whether it's in a canonical form. So loop strength reduce, first thing it does, it says, okay, I've got a loop, is it in simplified form? And then it collects chain. What is collect chains? What it does is, for every basic block in that loop that it wants to loop strength reduce, it calculates the SCEV expressions and collects them like in a bag to know what to do with them. It does a lot of transformations, and you can relate to it like you got a bunch of formulas and you want the minimum amount of formulas that you need to do the computation that you needed, because you want to simplify and have the minimum amount of computations. So it goes through these steps, but don't worry, I'm going to take you through the steps more or less with an example which is much easier to understand, right? So I'm going to look at loop strength reduce and those things we saw before with this example. So it's no coincidence there's a CI here and a CI here, because we want to see how it magically uses a commonality between these two. So the first thing it does, takes the LLVM IR and does what it does best, builds the SCEV expressions for it. So, sorry, go back to here. So you got a C times I, Ci plus K. That's all we need to care about right now, Ci and Ci plus K. So it comes here, it has the SCEV for I, the SCEV for Ci, it just folds it, so that's your SCEV expression. And from Ci, because it's using in two places, Ci as an address and as a computation, so you've got these two paths, and you have the store of instruction. So this is also called in loop strength reduction terminology the head of the loop. So it really starts looking at this and sees and goes back and sees what do I need to come. So it wants to store something at a particular address. So what do I need to store? Where do I need to store? So it has collected those chains, right? So that's what you see here. The SCEV expressions for the chains. So one is, this is the value to store, this is where to store, and this is the comparison, the loop induction variable to branch out of the loop. Okay, before I bombard you with that. So what does it do next? Once it's done this collection, it wants to know what common expressions I can use so I do minimum amount of computation. And it does this by refactoring. So what you see at the top is an expression, and the rest are exactly the same, just written out in different ways, and has really done that to see what's common. So if you look here, for example, you've got 12C. Where is 12C down here? It's somewhere folded in here, 4 times 3 and C. So these are all the formulas that it has. It has a cost function. This is doing its thing. So loop strength reduction is like 10,000 lines of code, and it's doing its thing, but it's using SCEV expressions everywhere. And this tutorial is about SCEV, so we're going to focus more on that. But there's a lot more to loop strength reduction that it does. It does its own optimization and stuff. The final solution comes after it has done all the cost analysis and stuff, is it has this SCEV expression. It has factored out 4, so the yellow thing that you see is common thing, is going to have just one register in which to store the expression. It's going to multiply it out, and the induction variable, and that's your final code. So what do we see here? So that's the expression that it got. The base that you see 3 times C, that's loop invariant. The start is loop invariant, so it has hoisted out of the loop. It's out of the loop, and in here it's doing this add by C. So that SCEV expression is getting computed here. Start value is here, it comes in as %1, and every time it's increments by C. So that's the magic it's doing. So we looked at a big user of SCEV. Look at some other users. Now, if you have two memory references and you want to know the dependence between them or dependence distance, sometimes if you want to interchange, for example, if they are, so stride, suppose stride is constant and known, and C1, C2 are two constants, so actual integers, you can ask SCEV, is SCEV a constant? So what you can do, literally, this is actual code. I've just deleted a bit of it from dependence analysis. You get the strides, so you get the SCEV expressions, and you do subtraction here. You ask if it's a constant, and so on. Let's take a real example, much easier to relate to. So here you're reading even locations and writing to odd locations. The SCEV would be this, so 0 plus 2, and this is SCEV. And this code will just go through these values and figure out, okay, there is no dependence because, yeah, you're reading from even values and writing to odd. Yeah. The other massive user of SCEV is vectorizer. And you've got a bunch of loop vectorizer, SLP. They use SCEV for simple things like induction variable, trip count. The loop vectorizer uses loop access analysis, which in turn uses SCEV massively. So again, with an example, so you're reading from A with a stride of k, so stride of k, and you're writing with a stride of k, so k times I. But there's an offset of nk. So these are non-overlapping. This is what's happening. So these are the green ones are what you're reading with a stride of k and writing to this. Of course, we can see here, okay, there is no overlap. But what does SCEV do? Again, does what it does best. First thing, so in the loop access analysis, you get the SCEV expressions. So that's the SCEV for this one and the SCEV for that one. And then loop access analysis is going to do some checks, tries to put some sanity. Are the strides the same? The strides are it's a k here, and if they're the same, then it's going to say, okay, I can work more with it. The strides were different, and say, okay, there is dependence. I'm not going to analyze it further. It depends how you implement the pass, what you do there. In this particular case, what it does really is it takes k equal to 1. It assumes k is 1, and does some analysis and says, okay, at least for k equals to 1, I can tell you there's no dependence. And it puts a SCEV predicate. So then in your actual code, you'll have an if k equals to 1. So when you actually get called, foo gets called with k equals to 1, is going to vectorize it, otherwise it won't. I mean, it's a limitation of SCEV, but of loop access analysis, actually, you could say like that. So we looked at a number of topics, basic recurrence, chain recurrences, users of SCEV. We're going to now look at some smaller topics that might be interesting. The first one is trip count, pretty straightforward. So if you have a loop, and a lot of parsers want to know how many times do you execute the loop. Now in this case, okay, we can see it's 100 times. The package actually is 99, so in the passes they add +1 to get the trip count. And if you ask SCEV, yeah, it tells you what you already knew, the package count is 99. What about some other interesting cases? So let's have a race between a rabbit and a tortoise. The rabbit starts at 0 and hops by 4. It's very fast. Tortoise is a bit slow, so it gets a head start. Okay. Now we want to know when does the rabbit, because the rabbit is going to overtake. When does the rabbit overtake the tortoise? So if you write it as a program, you could write something like that. You have a start values, and your SCEV increments are here. If you ask SCEV analysis, what's the package count? It says unpredictable. Not really unpredictable, right? Just 1, 2, 3. Now, this is just LLVM and SCEV, these are themselves evolving. So this is currently not possible, but one of you may want to go in and write a patch that gives you the value that you wanted here. So far, we have kind of looked at recurrence as start value plus a step. Actually, if you read the papers on recurrences, it's not limited to that. What if you have induction variable that's actually double? So you start with bit equals to 1, and every time you're doubling it. If you think about it, the SCEV for this is pretty obvious. So you start with 1, every time take that, multiply it by 2, and that's your SCEV expression. Current LLVM SCEV does not handle this. So if you look at the SCEV analysis, it says, yeah, it's 2 times bit 0. In effect, it says that I have not computed all of it. Okay, now the argument is, how often do you have this case? Yeah. And we can have endless discussions on this. But what, again, you could go and put in a patch which gives some kind of support for this and gets triggered whenever it's needed, right? So with that, I like to conclude saying we learned a lot of things about the SCEV. Not everything. There are a lot of things I had to leave out because it gets into more depth and you need to, and we have limited time. So we learned SCEV, how to construct SCEV expressions, how to simplify them, fold them into something beautiful that you give to parsers, and they love it and they use it in a way to generate optimized code. And we saw some limitations of SCEV. With that, thank you very much.
So we have around 9 minutes for questions.
Thank you for your tutorials. It was really interesting. My question is that we've seen rewriting rules for arithmetic operators. Does there exist rules for binary operators in this way?
Yeah, so you mean like and ors?
Yeah.
No, there is not. So if you look at the SCEV types that are expression type, you have and, or, and, multiply. You can do max and stuff, and cast. But so to say that you can, but it's very limited. So one example is like if you're doing a sign extend and a truncation, it checks ultimately what you end up with, and it can simplify it, remove. So if you have a sequence of truncates, for example, it's going to simplify it. But yeah, you're right. It is not for.
Is it a mathematical limitation or it's this implementation?
Yes, that's a good question. So to be honest, when I was thinking about giving this tutorial, I went back, read a bunch of papers to the point like, okay, it becomes more and more mathematical. None of the papers I saw for operands. So I saw for multiply, so we looked at add, we looked for multiply, exponents, but not for logical operands. Okay. Yes? Amara? Oh yeah, sorry.
Yeah, thanks for the tutorial. So you mentioned get SCEV at scope, right? Which eliminates basically add loops or add recurrences from a given SCEV in order to express it at a different point, right?
Yes.
But last time I looked at it, it could silently fail to do that. So you could, like you say, get SCEV at scope, and it did eliminate all of the, because it couldn't. It can only eliminate if it knows the exit value, right, of an add recurrence. And if it doesn't, it just keeps it around, which is like, let me put it like that. It's a bit annoying that you have to first specialize it for a scope and then check if it actually did in order to continue.
Yeah.
Which is
yes.
Unclear to me. Is there any efforts to change that, or is there a good reason to keep it that way?
To be honest, I didn't encounter that particular one. So I've seen used SCEV at scope, and in certain contexts, of course, it does work. But yeah,
sure.
Yeah.
If it works, all is good.
But there might be cases where it doesn't work. I'll give you what you need. Yeah, we need to discuss. Yeah.
Yeah, I think on your last example with the bit, I can't remember which pass does this, but surely you can generate a canonical induction variable in turn.
Sorry, could you speak louder?
If you go back to your last code example, it was pretty quick. I can't see.
This one?
Yeah, so for this one, I mean, SCEV may not be able to analyze the induction variable, but I think there's something else in LLVM that will generate a canonical induction variable and express that as an expression in terms of another IV, right?
Sorry, I didn't really get the question.
Or I could be misreading the code, actually.
Yeah.
Oh, and another comment is that there's things like SCEV expander, using SCEV to not just analyze but also generate IR code from SCEV is a pretty big use of Scalar Evolution, loop vectorizer, or generating versioning checks and stuff. So I think that's also a good thing to know if you're a client of LLVM, that you don't just have to use this as an analysis pass. You can also use it to just generate code once you've done some analysis.
Yeah. I guess you're referring to the expander, or yeah.
Are there any plans to extend support to loops with multiple exits, like side exits, where you actually know boundaries, but also you have some control inside? And, well, a lot of optimization depend on this Scalar Evolution, so it just bails out and completely skips them.
Sorry, I didn't get the question though.
So you're shown that you only support single exit, right? So what actually stops you from supporting some side exits, at least for the certain patterns of them?
So don't know if you so in simplify from a canonical form, you can have only one entry and one backage, but you can have multiple exits.
Okay.
Multiple exits is not a problem. I don't know if that answers your question.
That's not exactly what we see, how it works.
Okay.
We do use SCEV for inductive variant combination a lot, and well, my colleague that works on that, he constantly swears on SCEV, in particular because well, there are issues with caching. And
yes.
Do you believe these are like the innate design issues, or just some bugs that eventually need to be fixed?
You mean the caching of these SCEV expressions?
Caching of these SCEV expressions,
yes,
in order to make them faster. These caching sometimes does strange things like changing, sign, non-sign.
Yeah, yes, that's true. I have seen that. It's not surprising. Yes.
So, is the problem in the design, or
Yes, I think the problem is in the design. Yes. Yeah, I think SCEV has to be improved. It's good. Yes.
Maybe to add to that one, a question. So do you think, in retrospect, is the pointer equality on SCEV expressions important to have or not? So you could, like the caching and all of that is basically needed to get pointer equality on the same SCEVs, right? Which you're still not guaranteed.
Wouldn't you agree? Like, because it's not mutable, like it's, you really...
Wait, is it what you really want to have, or would it be fine to just have an equality function that says, okay, given to SCEVs, it will check for equality and tell you true or false?
I think based on what I've worked many months on it, the way it's going to refold, and every time it tries to simplify the expressions, it's going to call back everything, and if it didn't have this pointer comparison thing, the computation would be very large. I mean, it's going to take much longer.
Okay.
I think. Yeah.
And what is outside of Scalar Evolution? Do the users require that?
No.
Because then
yes, it does not.
So I'm aiming at. We currently have Scalar Evolution to get information about recurrences and a lot of other things, and we don't have an alternative. And if we want to have an alternative, we need an interface, and if that and the users should use that interface, and that interface should promise certain things. And pointer equality is one of the things I don't.
Yeah,
necessarily see
yeah.
alternatives to provide, because it's hard. There's a lot of maintenance effort, a lot of caching, a lot of downsides also. So if the users don't need it, that might be an idea.
True. Yeah, it's not in the contract that. Yeah, but I mean, we need to discuss. But I couldn't see how, without that powerful thing, it would be possible to limit the compilation time, because every time it calls back and wants to evaluate all over again.
Wait, I don't need to change SCEV. I just don't want it to be part of the contract to the outside.
Yeah.
If SCEV wants to do it that way, sure.
Yeah, I see. Okay. So that's yes.
That's okay.
I think that's a good idea. Yeah.
So we have run out of time. So let's thank Javed once again for this
Thank you.
tutorial.